Actually, before we do another example, we should talk about what does the integral mean. We talked about how to compute it. We want to ask ourselves, what does the integral mean? And there are two main meanings. One of them is if f of t is the rate of change of some quantity. That's what we had before when we knew how fast the city was growing or how fast the fly was moving. If the function we're trying to integrate is the rate of change of something, then the integral from a to b of that function gives the total change of the quantity from the beginning to the end. Note that it's not the total change in f. It's the total change in the quantity that f is the rate of change of. That was our motivation in coming up with these. And that first one we did about the city is growing this fast for this long and then this fast for this long is the best example of that. We knew the rate that the population was growing at over all those years. We combined those to find out, well, how much did the population grow over all of those years? Or the fly example was, we know how fast the fly is moving from t equals 0 to t equals 3. We add that up and find out how much did the fly actually move from t equals 0 to t equals 3. And in both of those cases, we end up knowing the total change in the function, but not the value of the function. We know how far the fly moved, but unless we know where the fly started, we don't actually know where the fly ended up. Unless we know the population of the city at some point, we don't know the population at any time. Just that over those 12 years it grew by this much. We know the fly moved a total of... Actually, how much did the fly move? We didn't know. What were we computing for that fly? Well, we'll get back to that. There's a second interpretation of the integral that's the way more common one. And to understand that one, we want to think about a graphical version of what were we doing. We have some function, f of t. We have an interval from a to b. We're cutting that interval up into subintervals. For each of those subintervals, we're choosing a point. For this drawing, I'm going to choose the left endpoint. We take the left endpoint and we say, what is that y value? We take all these left endpoints, we plug them all into the function. What did we do with them after that? We took those y values and we multiplied by the width of the interval. Well, when you multiply a height by a width, I know what you get. You end up with the area. When we take this height and multiply it by that width, you end up with the area of this rectangular strip. And then we wound up with the area of this rectangular strip, and this area, and this area, and this area, and this area, and this area. So the Riemann sum we were getting was take that height, multiply it by that width, add them up, gives us the total area. This area is the left-hand Riemann sum. It turns out to be a lower sum, because in all these cases the point that we chose, or the left end point, was the lowest point on the curve the whole way through. If we had used the right-hand endpoint, then we'd have this rectangle, and this rectangle, and this rectangle. It would be an upper sum. We would be adding on this area to the whole thing. Well, if I think about what am I estimating when I do this, let's cut it down to just 4 subintervals. that upper sum contains the entire curve. We're above the curve the whole way through, right? Let me pause and get a good. So our underestimate is these bars, which are underneath the curve the whole way. Our overestimate is these bars, which are above the curve the whole way. What is it that's in between? The thing that's in between is the area under the curve. Our overestimate turns out to be a number which is bigger than the area under the curve. Our underestimate turns out to be something smaller than the area under the curve. If this and this are very, very close to each other, then they will be this close to this, which is the area under the curve. This is the most common interpretation of the integral. We say the integral from a to b f of x dx gives the area under the curve. And above the x-axis. Between x equals a and x equals b. Which makes sense. So this explains why the calculator was graphing that goofy thing that it did. When it computed the integral from 1 to 5, it's shading that in, giving us a visual illustration of what is the thing that it's doing. I put an asterisk here on under because there's something a little bit more complicated, which is think about what happens if the function becomes negative. When the function is above the curve, I think of this function as having a positive rate of change. The function is increasing. I'm finding how much did it increase by. When the function goes below the x-axis, well, if my function was the rate of change of something, which is what I imagine it to be when I take an integral, that means that the thing that I'm got the rate of change of was decreasing. In this example, some quantity increased by a lot and then decreased by a little bit. And when I find the total change, it's going to be the net change. It increased by this much, but then decreased by this much. This will be a positive change in the function value. This will be a negative change in the function value because it was decreasing. So you increased by some smaller amount than that big amount. So the thing we end up doing with the area under the curve is the fact that this asterisk is that area below the x-axis counts as negative area. Which feels bad from a geometrical perspective. You very rarely have reason to count anything as negative area. But when I'm talking about doing a Riemann sum, I'm adding up a bunch of negative values. I'm adding up these positive ones and these negative ones, multiplying it by the delta x is going to leave it negative. You end up with a smaller number. So for example, if this is 1, and this is 4, and this area is 10, and if this area is 3, then the integral from 1 to 4 of that function is going to be 10 minus 3. The positive area is 10, the negative area is 3, 10 minus 3 is 7 would be the definite integral. Hey, let's go back and do that fly example. We were approximating the integral. So that fly example. We approximated the integral from 1 to 3 of x squared, right? Our best estimate was that our answer was somewhere between 7.9 and 10.15. What is the actual value? To get the actual value, I want to graph the function.